So this weekend I was sitting with my daughter, my 5-year-old daughter, at some sort of sandwich restaurant eating a sandwich and some chips. And we were basically fighting over who would get the chips. It's hard to explain to a 5-year-old. And I began to wonder, why are these things so addictively delicious? And it dawned on me, maybe one reason is that they're so brightly colored. They have an unnatural orange color to them that looks more intense than any natural food ought to look like. And so when you turn around the package and you look on the back side, you can see that there's a lot of stuff in here that doesn't look like corn. But in particular here, you get to this section called artificial colors, and it says yellow 6, yellow 5, red 40. And those words sound so simple, it's hard to imagine what those could be. You can't, obviously those are chemicals of some kind, but you can't say anything about what the structure of those molecules are just based on those names. And so I got interested in what it was that I was eating. Yes? Is what? It may be, in fact, yes. Allura red, you may know that. Okay, but none of those names mean anything to me. I'm a chemist, so I want to see structures or IUPAC names that I can derive stuff out of. And so let's talk about what the structures of those molecules might be there. So here's the structures of those chemical compounds. There was something called the U.S. Food, Drug, and Cosmetic Act that standardized the names of chemical dyes that are approved for use in human foods. And so there's a long list of chemical dyes that are approved. And so sometimes the names are shortened to FD&C, so Food and Drug and Cosmetic Act yellow 6, FD&C red 40, FD&C yellow 5. And I think that that's a lot more appetizing than the IUPAC name, 5,2-methoxy, 5-methylsulfonyl azole, 2-naphthalene sulfonate. And I'm not afraid to eat chemical compounds that are synthetic, but I'd like to know what those compounds are. So I wish they would put the long names on the package instead of these mysterious short names. I'll draw your attention to the structures here that are making these chips such a bright orange. Obviously it's not just one colored compound. They use a mixture of 3 different colored compounds to get just the right coloration there. So here's a yellow compound. And in particular here, what I'll draw your attention to is this functional group called an azo linkage. And you haven't seen that before, and it may look very mysterious. But by the time you get to the chapter on amines, chapter 25, we will show you how to make these compounds and how to synthesize them. Here's another compound, this FD&C red 40. Again, it's got an azo linkage between 2 benzene rings. So in chapter 18, we're going to be all about benzene rings and teaching you how to make bonds to benzene rings, just like this bond right here. We'll show you how to make that bond. And again, the third compound has an azo linkage. It's a little bit more fancy, but it's basically, this is like a benzene ring with an azo linkage. So in chapter 18, we'll show you how to make bonds to benzene rings. And then in chapter 25, we'll specifically show you how to make this kind of carbon-nitrogen bond. So you can see how these types of colored compounds are made. And yum, yum. Next time you open up a bag of chips, you have a clearer idea of what's making those so delicious looking. I can't wait to look at the Cheetos bag to see what's on there the next time I grab one of those. Okay, so we just had an exam on Friday, and you guys did fantastic. It was out of 128, so we posted the scores on EEE, and when we initially posted those scores, we accidentally left the default out of 100. The exam was not out of 100, it was out of 128. And your score that's posted on EEE is out of 128. Multiple people made perfect scores, 128 out of 128. Great job. The mean was 88 with a standard deviation of 23. Great job. You guys did great. And keep working hard. We've got about 2 weeks left before the exam. And remember, my advice to you was drive thy business. And so it's not the week before the exam that's going to matter. It's what you're doing today and tomorrow and the next day and this weekend. So you need to be on the material this weekend studying like the exam is on next Monday, even though it's not. This is the time when you need to really be bearing down on the material. Okay, so we're going to step into a new chapter. We just finished this chapter on radicals, and there wasn't a whole lot to cover in the chapter on radicals. And likewise, there's not a huge number of concepts in chapter 16. We're going to take today's lecture and a little bit of Wednesday's lecture and cover chapter 16, which covers dienes, polyenes, resonance. Basically things that have to do with double bonds connected to things. And so let's go step into chapter 16 in the Gorzinski-Smith textbook and see what that's all about. So one of the major themes in chapter 16 is this idea of conjugation. And so let's talk about conjugation. What does that mean? I think the best way for me to explain conjugation is to draw out a molecule that has this property of conjugation in it. And so here's a 5-carbon molecule. It's not pentane. This is pentadiene. It's a 5-carbon chain with 2 alkenes in it. And you'll notice that the 2 alkenes are right next to each other. And they're separated by a single carbon-carbon single bond there. So this is an example of a molecule that is conjugated. I would refer to this broadly. If I were to just point over there, I would refer to this as a conjugated diene. And I would contrast that from some sort of a diene where the 2 double bonds are way apart from each other in different parts of the molecule. So to help you see why I described it as a conjugated diene, let me contrast that with some dienes where the double bonds are not conjugated to each other. So now I'll draw a longer molecule. This time I'll draw a 6-carbon chain. And I'll draw another alkene somewhere way over here on the other side of the molecule. That's not conjugated. That's a great example of a molecule. It's a diene. There's 2 alkenes in there. That's a great example of a diene in which the double bonds are not conjugated. So not all dienes are conjugated. Let me take an even simpler example of a 5-carbon chain. So you can better contrast this with the 5-carbon chain over here. Here's a 5-carbon diene, and that's also not conjugated. So we refer to these dienes, we describe that relationship between the double bonds as that those double bonds are isolated. So these are definitely dienes, but these are isolated dienes. And maybe you're having a hard time seeing that those double bonds aren't connected. It might help you if I drew the CH2 in between. So you can more clearly see, no, those double bonds are not connected to each other in any way. Okay, so 2 types of dienes, or 2 classes, or 2 ways to think about the relationship between the double bonds. Conjugated versus isolated. And obviously I'm making a big deal about this because there must be something special about one of these, and it's the conjugated dienes, or trienes, or pentaenes. It's when you conjugate double bonds that you give molecules special properties. Okay, let's go ahead and talk about not a double bond next to a double bond, but we'll talk about a double bond next to a carbocation. And so I'm going to talk about the prototype of a system in which there is resonance, in which there is a property that is a little bit related to conjugation. Actually, let me draw C's on here. I think this might help us to see what's attached. And I'll draw one more CH in the middle. So this is a 3-carbon allyl system. We've talked about allylic halogenation. This is an allocation. And let me draw another resonance structure of this so we can see that, in fact, that positive charge, that lack of an octet, is shared on 2 different carbon atoms. And I'm going to use arrow pushing to help me see how to get to the other resonance structure. So there's another resonance structure, and what I'll do is I'll take this pi bond and I will swing it over here like this. This is the way you depict this with arrow pushing, to show that I'm creating a new double bond over here. If you move the double bond over and attacked that carbocation, that would be an equally good depiction, just as long as you're precise. So I'm drawing this double bond shifting over to make a new double bond on the other side. In other words, I'm taking electrons away from the carbon that's on the left-hand side. So let me draw out that resonance structure. When we draw resonance structures, we always use these 2-headed resonance arrows. I don't draw equilibrium. This is not an equilibrium between 2 structures. These are the same molecule. I'm just showing you 2 different ways to depict it. These are 2 different depictions of exactly the same molecule. So what this picture predicts for me is that carbocation, there's 50% carbocation character on the left carbon, and there's 50% carbocation on the right carbon. And one of these resonance structures is not better than the other. Watch, let's practice resonance arrow pushing to see resonance structures by going back to the other resonance structure. I'll take this double bond and I'll shift it over, and I will precisely end on that CC single bond. So that's an example of how to use arrow pushing to depict resonance. And so once again, these are not 2 structures equilibrating. They're just 2 different depictions of a single structure. So You were already taught about resonance back in chapter 1, so if you want to review that, you can go back to section 1.5 about what resonance arrows are all about. But starting right now, we're going to see a lot of resonance. In chapter 16, we're going to see a lot of resonance in allocations. In chapter 18, you are going to be drawing allyl-type cations and resonance-stabilized cations over and 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 over again. So, so it's good to have an introduction in this chapter. Okay, so resonance, like allocations, and conjugated dienes. That's a big theme in this chapter. That's what we're all about. Okay, so let's talk about resonance. Things don't have to be allocations, but they can be. What I'm going to do is I'm going to show you some types of, not mostly chemical reactions here, that lead to resonance-stabilized systems. So I'll start off with this allyl bromide here, this allylic cyclohexenyl bromide. And you learned how to make that through a free radical bromination, N-bromosuccinimide in the last chapter, and use light or peroxides or some sort of initiator to get that going. So you learned about how to make these types of allylic bromides. If you put this into a polar solvent, it will stabilize carbocation formation. So you can get SN1 reactions out of this. And so let's draw out the intermediate, the carbocation intermediate that you would get out of this type of an SN1 ionization. And I'll start off by drawing this resonance structure here, where I put the carbocation right there where the bromide left. So the bromide anion leaves and leaves the carbocation. But there's another resonance structure I can draw that's equally good. I don't see the full picture here. This picture makes me want to attack this carbocation on the right-hand side, but there's an equally good resonance depiction that I should draw because it will help me see that there's an equally good probability that the nucleophile will attack on the left-hand side. And by drawing those two resonance structures, it helps me to see those two choices with great clarity. So I urge you, when you can, to draw two resonance structures, two resonance depictions of the same molecule, because it will help you see those choices in reactivity. Okay, not everything has to be a carbocation. Let's take an example of an acid-base reaction. So this is a carboxylic acid. You're going to have an entire chapter on carboxylic acids, chapter 19 in the Gorzinski-Smith textbook. If I expose a carboxylic acid to a base, well, that's an acid, and this is a base. I'm symbolizing the base with the letter B. You should probably expect that that base is going to abstract a proton to pull off a proton and leave a negatively charged carboxylate anion. So again, this is chapter 19 all over. You're just going to have an entire chapter on this, on making carboxylate anions. And so let me draw, and I'll draw all of the lone pairs on that oxygen. So there's an O- that you generate, but there's an equally good resonance depiction for this molecule. Let me draw that other resonance structure. And I'll use resonance arrow pushing here to help me see how I get back and forth. Let me take, I've got too many electrons here, and so I'll take this oxygen lone pair, one of these three oxygen lone pairs, bring it down to make a CO double bond. But I don't want to have 5 bonds to this central carbonyl carbon, so I'll pick up one of those pi bonds and I'll give it to oxygen. And that helps me see how I should depict this other resonance structure that's equally good. So here's my other resonance structure. I've got two equally good resonance structures. Two equally good resonance depictions. Maybe it's bothering you that I didn't put the 2 lone pairs on the carbonyl oxygen, so I'll do that here. There we go. Oh, that's satisfying. Look at that. Okay, so those are two equally good. Neither of these two resonance depictions is better than the other. They're both equally good resonance depictions for a carboxylate anion. And so this is another example of resonance that helps us to explain why carboxylic acids are acids. Why are they so acidic? It's because this anion is resonance stabilized. The negative charge is distributed on 2 electronegative atoms and not just stuck on 1 electronegative atom. Okay, here's an example of another type of reaction. And this would be an example, gee, I wish I'd drawn that in red like I did everything else, but here, let me try to trace over that in red. Here's an example of probably the best type of SN1 reaction you'll ever see. It's better than any SN1 reaction that you saw in chapter 8. Right? All the SN1 reactions you saw in chapter 8 were lousy. But this is the kind of SN1 reaction that you'll see when you get to chapter 22 or 21. And I'll show you why this one is special. It's because the carbocation that you generate in this process is better than any other kind of carbocation you have ever seen before. Let's draw that carbocation. And maybe that doesn't look very spectacular to you. I guess it doesn't look spectacular to me either. But if I draw the lone pairs here, it reminds me that those oxygen lone pairs can donate over into the carbocation. And I'll depict that by making it form a pi bond here. And this is an extraordinary resonance structure. I love this. It's so satisfying. Oh, there's another lone pair here. I'll draw that. It's not really important. The important part here is that when I draw this other resonance depiction, every second row atom has an octet of electrons. Right, now that's a good cation. Better than T-butyl or anything else you've ever seen before. Better than benzylic. Okay, so the last example is not a chemical reaction. I'm just going to remind you that carbonyl groups, any carbonyl group, we can depict with another resonance structure. So every time I draw a carbonyl group, I have to remember that oxygens are electronegative. And so it just makes me want to pick up the electrons in that pi bond and give them to oxygen. If oxygen is so electronegative, gee, shouldn't this molecule behave like the oxygen has more electrons? Let's draw that resonance structure. There we go. Oh yeah. In other words, carbonyls behave like carbocations. Nucleophiles want to attack the carbonyl carbon. In the Chem 51LB lab, you did a reaction where sodium borohydride attacked that carbonyl carbon, and that resonance structure explains why. Okay, so let me label these several different systems because these are kind of the point of chapter 16. The first half, 80% of chapter 16, either good or bad, has to do with allyl cations. So that's an example of an allylic cation or an allocation. Here where I have two oxygens and a negative charge, when you deprotonate a carboxylic acid, you generate a carboxylate anion. Whoops, I'm running out of room there. I think you can see that, carboxylate anion. You can have allyl anions, they're just not very common. And you're not going to see them anywhere in the Chem 51 series, so I'm not going to draw that for you. This is a more common form of anionic resonance, the carboxylate anion. This species right here, they have two different names for these two different resonance structures. So for example, over here, I would call this, the technical name that you've never heard of is going to sound really weird and fancy. Don't worry about this, I don't expect you to know this. But this is called an oxocarbenium ion. This resonance structure, this resonance depiction is called an oxocarbenium ion resonance depiction. And you don't need to know that. Don't write it down, just trying to impress you, I guess. This one over here, you do know the name for that. Oxygen with 3 bonds, there's a bond here to the methyl. Oxygen with 3 bonds is called an oxonium ion. So this resonance depiction is an oxonium ion resonance depiction. Oxygen with 3 bonds always has a positive charge. And you've seen oxygen with 3 bonds before, like a H3O plus, a hydronium ion. That's an oxonium ion. And then this last one we don't really have a name for. That's just a resonance structure for a carbonyl group. Okay, so these are examples of resonance and how we can use arrow pushing to go back and forth from one resonance structure to the other. And I'll expect you to be good at that. So practice doing that. It's important, and it helps us to see how resonance can stabilize carbocations, resonance can stabilize anions, and those are major themes for this chapter. Okay, whenever I've got, let me just keep this picture here, and I want to draw these attention to these structures here and ask, when you've got two possible resonance structures, how do you decide which of those two resonance structures is better? Which one should you draw on the paper? Which one will help you to predict reactivity? I've got these two resonance structures for acetone. You've been drawing this structure over here on the left-hand side. But when I draw these other two resonance structures, an oxocarbenium ion depiction versus an oxonium ion depiction, which one should you be paying attention to? Well, in truth, you should be paying attention to both. But let me give you a pair of 2 rules, and it's only 2 rules you need to apply to help you decide which of these two resonance structures is most important. And maybe it depends on what you're trying to see is what will decide what's most important to you. So here's two rules I'm going to give you that will help you to rank resonance structures. What's the first best resonance structure, and what's the second best resonance structure? And I'll start off by drawing a species that's a little bit ahead of our time here, but this is a resonance structure that's going to come up in a big way in chapter 20. Okay, so here I'm going to draw this very weird species that should look a little bit to you like a carbonyl group, but it's not a carbonyl group because there's a double bond to nitrogen. And whenever I have 4 bonds to nitrogen, there has to be a positive charge. That will be more plain to you when you get to chapter 25 on amines. But for now, maybe it's not so obvious to you, but it is true and it's helpful. Okay, 4 bonds to nitrogen, there must be a positive charge there. There's another resonance depiction I can draw for this. This species is called an iminium ion. And you'll see a lot of this in chapter 20. So let me draw a resonance depiction for this. It's just a different way of depicting this molecule. And I'll start by giving the electrons here to the electronegative atom. That's nitrogen. Nitrogen is more electronegative than carbon. And we haven't done a lot of nitrogen chemistry yet, but you will. And so when I draw this other resonance depiction, it's kind of like that carbonyl group resonance depiction. I'm going to draw this as a carbocation. And when I draw this, now the positive charge is on carbon. So 2 different resonance depictions. And how do I decide which of these is a better resonance depiction? Rule number 1, whenever you look at 2 resonance structures, and it's a very simple rule, is the best resonance structure has the most bonds. What a simple rule. Now don't draw extra bonds that don't belong and violate the octet rule, but I've got 2 resonance structures. They're both valid Lewis structures. And when I look over here, the iminium ion depiction has more bonds than this other carbocation depiction. And so that's the best resonance structure, the one with most bonds, this one over here with 5 bonds. So I'll rank this as, this is the number 1 best resonance structure, and this would be number 2. And why would I care about which resonance structure is the number 1 resonance structure? Whenever I draw some box on my exam and I say draw the product in the box, I expect you to draw a stable form of a molecule. You have been drawing the number 1 resonance structure, a carbonyl group. You'll draw an iminium ion. The other reason why I should care about this best resonance structure is the best resonance structure explains the hybridization and shape. In other words, if I look at number 2 resonance structure over here, I might think that this nitrogen with 4 different substituents, one of them is a lone pair, might be pyramidal. But that's not true. Iminium ions are flat. This is the resonance structure that depicts for me that nitrogen is sp2 hybridized and flat. It's the best resonance structure that predicts the shape of this molecule and the hybridization of nitrogen. So look at the best resonance structure if you want to predict the shape of a molecule and the hybridization of the atoms. You look at the best resonance, and that's typically what you've been drawing. You've been drawing the best resonance structure. Let's take an example of another pair of structures. And this time what I'll do is I'll take an alkene. But I'm going to put a substituent on this alkene, not the R. That's not very exciting. I'm going to put an alkoxide anion substituent on this molecule. And this should look very strange to you. What is that? Alkoxide anion. It's actually a deprotonated enol. And you're going to have an entire pair of chapters on this. Chapters 22 and 23 in the book will be all about this type of a structure. So let me help you draw a resonance structure for this. We'll draw another resonance depiction. And to help me see how to get to that other resonance depiction, I will start by taking these electrons on oxygen and pushing them downward to make a pi bond here. Well, I don't want to have 5 bonds to this carbon, so I have to break something. I'll break that pi bond and give the other electrons to the other carbon. So this is called an enolate, and again, you're going to have 2 chapters on enolates over and over and over again. Enolates until you're sick of drawing enolates, or else until you love enolates, because that's how biology works. So here's my other resonance depiction. And so now I've got two different ways to depict the same molecule. Two different ways to try to give me some clues about what's the shape of this molecule and how does it react. So rule number 2 is well, let's review rule number 1. Rule number 1 is which resonance structure has the most bonds. And if I count how many bonds this carbon has, it has 1, 2, 3, 4. And then I look over here at how many bonds that carbon has, it has 1, 2, 3, 4. If you added up all the bonds in these two resonance depictions, they'd be identical. Same number of bonds. So you can't use number of bonds to predict which of those resonance structures is better. If you go by rule number 1, they're equally good. But rule number 2 says, after you've satisfied the bond deal, then you look at, did you give the electrons to the more electronegative atom? So here, in each case, one of these atoms, one of these second row atoms has too many electrons, has an anion, has a negative charge. Over here it's oxygen on the left, and over here on the right, in this resonance depiction, it's carbon that has the negative charge. And I hope you know, oxygen is more electronegative than carbon. Oxygen is more electronegative than carbon. Based on that, I like this resonance structure better. And over here, I like this resonance structure not quite as much. But here's what's ironic and also powerful. If you care about chemical reactivity, if you care about forming bonds, and of course I care about chemical reactivity, and I care about forming bonds, and I care about predicting reactivity, it's the second best resonance structure that explains chemical reactivity. Isn't that ironic? When I look down over here, it's what this second best resonance structure on top does is it predicts for me that nucleophiles won't attack nitrogen, nucleophiles will attack carbon. It's the second best resonance structure that predicts that. If I really care about chemical reactivity, I'll draw out the second best resonance structure and it predicts that nucleophiles attack there. If I really care about which two ends of this system, the O- end or the C- end is more reactive, when this reacts with electrophiles, it reacts faster on carbon. And I'm just going to abbreviate electrophile with EL plus here. So pay attention to the first best resonance structure and the second best resonance structure. And it's that second best resonance structure that has the most predictive power for you. So let me just show you one, and I have very little room here. I'll try to squeeze this in. Sometimes, as in the case of that carboxylate anion, I'll draw two different cations for you. Here's an allyl cation. There's one resonance depiction for an allyl cation. And let me draw the other resonance structure. Or I put the carbocation on the bottom carbon. Those are two resonance depictions. They have the same number of bonds. In each case, the carbocation is on a carbon atom, so there's no difference there. Those are equally good. There's no difference. You can't look at that and decide one is better than the other. So if you were trying to rank these, well, you can't rank them. They're both ranked as number 1. They both have the same number of bonds. They both satisfy or dissatisfy electronegativity. So sometimes the two resonance structures are equivalent in terms of which one is better or which one is worse. And so you'll just have to draw them both and pay attention. Right? This picture here predicts for me that nucleophiles will attack either end with equal ease of that allyl cation system. Okay, so whether you've noticed it or not, I've been in my mind throughout this entire quarter so far thinking about the second best resonance structure and use that as a guide for predicting reactivity. Okay, so let's try to think about hybridization. And I regret talking about this in this chapter because you're not really going to use this piece of information I'm giving you until the next chapter. But we need to introduce this idea here of how resonance affects hybridization and shapes of molecules. And you'll use this in the next chapter, not in this chapter. So let's go ahead and start about talking about this. And I'm going to talk about something that I hope is totally obvious to you and is just so it'll help us see why this next part might be a little bit confusing. So what I'm going to do is I'm going to draw several different second row atoms in ways that have lone pairs on them. So let me draw a carbon with a lone pair on the carbon atom. And I'll simply remind you that when I do this, when I draw it like that, the carbon is going to have a negative charge. That's going to be a carbanion. But the important point is that this will prefer to be sp3 hybridized. So way back in general chemistry, you probably learned something like valence shell electron pair repulsion theory, or maybe it has some new name, fancy name nowadays. But it simply predicts for you that molecules like methyl anion or this homolog with nitrogen, in other words, ammonia, you had some set of rules that allowed you to predict that ammonia would prefer to be pyramidal. Not flat, not trigonal planar, but pyramidal. So in all of these cases, the central atom here is sp3 hybridized and pyramidal. sp3 hybridized and pyramidal. That's the preferred shape of that molecule. Let me do this last one over here. I'll draw out a water molecule just so I can march across the periodic table, carbon, nitrogen, oxygen, and now there's 2 lone pairs on there. And again, that's sp3 hybridized and pyramidal. That's the preferred hybridization for all of these 3 systems. And it doesn't matter whether I have 4 hydrogens on carbon and had methane, it's sp3 hybridized and pyramidal. Okay, but let's contrast this. What happens if I have a carbanion and there's a double bond next door? Your predictions will change. And that's what's strange. Your predictions that carbanions are always pyramidal will no longer be accurate. So in other words, when I come over here and I put a double bond on that carbanion, I think I left off a negative charge on there, so let me add that negative charge on my carbanion. There we go. Looks a little bit thick there, but that's a minus charge to go along with the carbanion. Now once we put a double bond there, it's not the same situation, and we once again have to decide what kind of orbital is that lone pair going to be in. Is it going to be sp3 hybridized, sp2 hybridized, or in a p orbital? And what kind of shape is that molecule going to adopt? The shape strictly correlates with the hybridization. Is that carbon with the lone pair going to be pyramidal or flat? And so really there's 2 extreme depictions of this. And the 2 extreme depictions are, one would be to have that lone pair exist in a p-type orbital, and that's totally different from what's above. The lone pairs above are in sp3 type orbitals, but you could draw it with the lone pair in a p-type orbital, same type of orbital you draw for a carbocation. Or you could draw that lone pair in an sp3 hybridized orbital the way we did above. Those are the 2 choices. And in order to understand the shape of this molecule, you have to ask yourself, if you really want this lone pair to interact with either pi or pi star next door, with a double bond next door, then you really want, because pi bonds have equal density on the top or the bottom, you really want the orbital that this lone pair is in to have equal size on the top and the bottom. Right? Over here, if I hybridize this lone pair in a p orbital, where it has equal size on the top and the bottom, I'll get equally good interactions with the top of pi or pi star, and equally good interactions with the bottom of pi or pi star. And so, why am I saying pi or pi star? It depends on whether I'm talking about a radical, or a lone pair, or a carbocation, but it's all the same idea. The fact is, you want this orbital to be hybridized like this with a p orbital there, if you want to maximize interactions with neighboring double bonds. And if you try to do the opposite, if you try to pyramidalize that and put those electrons into an sp3 orbital, you'll get great interactions here. Look at this big sp3 lobe up there. Oh, and look at that pi or pi star right there, the big interaction. But then you look at the bottom, and it's like this weak, pathetic interaction. It's totally losing out. So there's 2 choices here. If you want to have effective interactions between either a radical or a lone pair or a carbocation next door to a double bond, if you really want effective overlap, that would be this case over here. Whoops, that's supposed to say overlap. You get effective overlap. When you hybridize it with p orbital hybridization, you get effective overlap on both the top and the bottom of the pi system. But if you try to hybridize it as sp3, I guess I don't have a good word for this, so I'll call it pathetic overlap on the bottom. Yeah, it's great overlap on the top, but that doesn't make up for the fact that the overlap is pathetic on the bottom. So the bottom line is, if you got a double bond and then right next door you have a carbocation or an anion or a radical. That carbocation or anion or radical is going to be in a p orbital. And that carbon atom will be flat and trigonal planar because it's sp2 hybridized. And again, we're not going to use that in this chapter. You have to hold on to that idea until we get to chapter 17, the next chapter, and you'll use that. So just hold on to that idea. Okay, let's talk about chemistry and some chemical reactions. Well, I guess we're not quite ready to talk about chemistry and chemical reactions, but let me try to get you ready for that. Okay, I want to come back to this idea of dienes, conjugated dienes, systems in which there's two double bonds directly next to each other. And I want to draw a diene in two different conformations. So here's a molecule with 6 carbons, and I've just attached them in this funny way. And when I draw it like this, the important thing here is to recognize that you can rotate about this central single bond here. I can rotate about that bond. There's free rotation. There's nothing stopping that bond rotation. So when I draw that rotamer, that different shape of this molecule, and this is not a resonance structure anymore because I'm literally moving atoms. That would be totally inaccurate for me to call this a resonance structure because I'm literally taking this CH3 and moving those atoms over here. There's a rotation that's occurring. So I have to draw equilibrium arrows if atoms move places. In a resonance structure, the atoms do not move. So this can't be a resonance depiction. This is just an equilibrium between two rotamers. Both of these molecules are flat. If you want to have effective interaction between one double bond and the other, we call that conjugation, then the molecule has to be flat. The molecule has to be planar. And here's two completely different planar conformations. They're equally planar. All I've done is I flipped the double bond on one side of the molecule versus the other side, but they're both planar conformations. And we need some way to describe these two different conformations because they will behave differently when we do chemical reactions. And it's important that you recognize these two different conformations. There's a sigma bond between the two double bonds. And so somebody, I don't know who invented this system, decided we're going to call this system where the two double bonds are opposite sides of the single bond, or anti-periplanar, as italics S. I don't know how to draw italics S with a pen here, but that's italics S. This is called the S-trans conformation. S stands for sigmoid, or sigma bond in between. Right? We're rotating around a sigma bond. And this conformation over here is called the S-cis conformation. And again, it's an italics S. So when you see it typed out, it's an italics S. So this is the S-cis conformation. So two different conformations. And what we'll find is that one of these conformations, the S-cis conformation, does a very important and particular type of chemical reaction, and the S-trans conformation doesn't do it. Okay, let me contrast. It may look to you like, oh, that's E and Z. No, this is not E and Z. S-cis and S-trans are completely independent of E and Z designations of configuration. So when I look at this alkene on top here, these two substituents cause this alkene to have the Z configuration. They're on the same side. This is kind of the mnemonic you can use. So that alkene on top has a Z configuration because the high priority groups are on the same side as the double bond. This S-cis and S-trans is a completely different type of idea. The S-cis and the S-trans has to do with this single bond between the two alkene moieties. By looking at the relative orientations of those two double bonds relative to this sigma bond in between, I would call this the S-cis conformation. So S-cis and S-trans are completely different from E and Z. Don't confuse those with E and Z. E and Z have to do with substituents attached to double bonds, whereas S-cis and S-trans has to do with the relative dispositions of two alkenes that are conjugated to each other. Okay, so in chapter 16, in section 16.7 and 16.8, there's some fun stuff about interesting dienes that you can find in Nature or do it. That's fun reading. Or if you want to memorize some bond lengths, that's a great place for you to go. That's not the type of thing you've seen my exams and problem sets. That's not the kind of stuff I will ask you about, because all you could really do is memorize those structures or answer some multiple choice question. So, yeah.
Why is there an equilibrium error?
Because if you move atoms, let me just make it more clear. Over here I have H2C, and over here I have CH3. And now when I look over here, the methyl group is on the opposite side. This carbon is now moved into different positions. If you move any atom, if you move a single atom, it can't be a resonance structure. When you draw two resonance depictions, no atom can change places or move. The atoms have to be in exactly the same place when you draw two resonance depictions. So that can't possibly be a resonance structure because there's not three H's there. There have to be, otherwise that can't be a resonance structure. So atoms were literally moving around. When molecules change shapes, that's not resonance. When you have two chair forms of a cyclohexene, they're not interconverting through resonance. There's an actual reaction with an energy barrier involved with that. Okay, so let's talk about the arrangements of double bonds on dienes. So you'll read section 16.8 about fun molecules that have more than one alkene in them. And you can read some cool stuff about bond lengths. Those details are not necessary for us, but you should read them because they're cool things to read about. I want to give you two different dienes so that we can talk about them and compare them. And I'm going to give you two dienes that have exactly the same number of atoms, exactly the same molecular formula, and all we're going to do is we're going to change the relative positions of the double bonds in these molecules. And so over here I'm going to draw a six-membered ring with two alkenes conjugated to each other. That's a conjugated diene. And I'm going to compare and contrast that with a diene in which the two double bonds are not conjugated. They're not directly connected to each other. There's CH2 groups between the two double bonds on each side of this molecule. And the two things that I want to pay attention to have to do with the stability of the molecule versus the reactivity of the pi bonds. So the molecule itself, the overall molecule, if I were to rank the stability of these two molecules, then what I would say is that in comparison, the molecule in which the double bonds are conjugated is more stable. The overall molecule is more stable. And when the double bonds, same number of atoms, same six-membered ring, all I've done is taken the double bonds out of conjugation. In comparison, that arrangement is less stable. So conjugation of double bonds makes molecules more stable. Molecules are more stable when the double bonds are conjugated. So if you have a diene, the molecule is more stable. But I want to contrast that, not with the overall molecule, but just the pi bonds. Just the individual electrons in that pi bond. I've got all kinds of bonds in this molecule. I've got sigma bonds here, CH sigma bonds, but I'm just talking about the pi bonds. There's one up here, there's one down there. And if I just focus my attention on those pi bonds, what I would find is that the pi bonds in the conjugated diene are more reactive. And the pi bonds, when they're not conjugated, when they're isolated, are less reactive. And it's like, more reactive in what? Well, take any one of those reactions you learned back in chapter 10. Addition of HBr, addition of Br2, hydroboration, any one of those reactions, the conjugated diene will react faster than the isolated diene. So understand what I'm talking about. In this case up here, I'm talking about the whole molecule itself. But down below here, I'm talking about pi bonds. Now, let me point out why this is not normal, business as usual. For the first 15 chapters of this book, what you learned about for carbocations, what you learned about for radicals, and what you learned about for anions is that more stable is less reactive. So this diene thing, this conjugation thing, is the opposite of everything you've learned for 15 chapters. So let me just remind you of what you learned for carbocations. What you learned is that tertiary carbocations versus primary carbocations, you learned that the tertiary carbocation molecule here is more stable than a primary carbocation. You knew that. But somehow or another, you learned that carbocations are less reactive when they're more stable. You learned that primary carbocations are really unhappy and are more reactive. And the same would be true for an anion or a radical. There's this converse relationship that things that are more stable tend to be less reactive. And so now I'm telling you, for conjugated dienes, it's the opposite. Now more stable just happens to correspond with more reactive. And the way to understand that, once again, is that I'm talking about the stability of the overall molecule with all the C's and all the H's, whereas here when I'm talking about reactivity, I just care about the pi electrons. So you can have one part of the molecule be more reactive even though the overall molecule is more stable. If I take everybody on this side of the class and I say I'm going to give all of your points so far to the rest of the class, on average the overall class is more happy, even though this side of the class is very pissed off and very reactive. So on average the whole molecule can be more stable even if just one little part of the molecule is more reactive. Okay, so what would happen if you did some of your chapter 10 reactions on a diene? You added HBr to a diene or Br2 to a diene. Let's take an example of that. And so here would be an example that you already know about. That's addition of HBr across double bonds. There's two double bonds there, but I'm just going to talk about adding one equivalent of HBr. You'll get two different products out of this reaction. And maybe it's not totally obvious to you. We added H and Br. I'm confident you can all see the Br. Let me just remind you of where the H is so you can see it more clearly. There's the H, and there's the H. In other words, I ended up with an allocation and the bromide added to either end of the allocation. Let's go ahead and draw out a mechanism that will help us to more clearly see how that works. So I'll go ahead and draw it like this. I'll draw my HBr right here. And then I'll draw just some sort of arrow pushing to help me see how you get an allocation out of that. So when I use that double bond to pluck off a proton, and the double bond's going to protonate on the end there in order to give us an allocarbocation intermediate. So here's the allocarbocation that we get. And there's a bromide anion floating around there. Here's the bromide anion. So I hope you can see that it's kind of obvious here that you can get this product on top, the first product, by having the bromide attack. Now we've got two different products, and we've got a way to describe those. Whenever you have a diene system, you can number those carbon atoms in the diene with some numbering system. And the way we typically do that is 1, 2, 3, 4. And if we look at those numbers, in this first product here, the H and the Br are attached to carbons 1 and 2. We call that the 1,2 addition product. If I went to any organic chemist and I said, oh, I took this diene and I got the 1,2 addition product, they would know exactly what I'm talking about. The H and the Br end up next to each other. The other product that you typically get as part of a mixture has the proton and the bromine attached at carbons 1 and 4. That's called the 1,4 addition product. So that nomenclature, I think, is pretty obvious. And you typically get mixtures. But how do you explain the formation of this 1,4 addition product? The way to explain that 1,4 addition product is to draw the other resonance depiction, where I move the double bond over and I have the carbocation on the other end. And when I draw that other resonance depiction, I think it should be obvious how you get that other product. I get the 1,2 addition product if the bromide attacks one end of the allyl system, and I get the 1,4 addition product if the bromide attacks the other end of the allyl system. So typically, when you have dienes and you add HBr, you will get a mixture of 1,2 and 1,4 addition products. And there's this obscure, and this is kind of obscure, and it's not 100% general, but in the case of unsubstituted butadiene with no substituents, the 1,2 addition product forms faster. It forms 4 times faster than the 1,4 addition product. You get an 80 to 20 mixture when you take butadiene that has no substituents and you add HBr. And if you keep the temperature low. That's interesting. One of those products forms faster, and it turns out to be the major product. But as you read through here and you go, you read on in that section, what you realize is that allobromides are susceptible to ionization reactions, to SN1 reactions. So when you expose this to some sort of a polar solvent system, it makes it easier for this bromide to leave and generate an allocarbocation. And I'm not going to draw all the, well, here's one of the two resonance structures. I'm not going to draw both the resonance structures. So you'll get an allocarbocation intermediate, and then the bromide can attack the other end in order to give you this. And then it can go backwards. The bromide can pop off again, and then re-add to the original position. So this equilibrates back and forth. And when you allow allobromides to equilibrate, you will equilibrate them such that you end up with the isomer that has the more substituted double bonds. And this is just a general rule. Isomers with more substituted double bonds are more stable. And so that's why you favor this other product, more substituted double bonds equals more stable. This is nothing more than an SN1 type substitution where the nucleophile is the same as the leaving group. So in other words, if you allow this particular system to equilibrate, it's the 1,4 product that is favored. And the book seems to make this big deal about that, and I'm not sure why that's so important, but they consider that to be an important issue. Okay, I'm going to go ahead and stop there. And when we come back, we're going to cover a really powerful reaction called the Diels-Alder reaction. And it's a super powerful way for making 6-membered rings. And it will be on my exams, it will be on Susan King's exams, it will be on Zibin Guan's exams, all the other sections will all have these on our exams.